Hello, this is Josiah Winslow recording for his Programming in Java course at MATC for the rest of his classmates. Now, as part of your next assignment, you are going to make a rock, paper, scissors game. And for extra credit, you can make the rock, paper, scissors, lizard, Spock variant that was popularized on the Big Bang Theory. Now, there are many ways that you could do this. There are many ways that you can figure out who won a rock, paper, scissors game or a rock, paper, scissors, lizard, Spock game. One way is to do something like this, chaining together a whole bunch of conditionals and logical operators and if statement to basically spell out the result of pretty much every possible game that could possibly occur, which is very, very clunky and very, very hard to make, but it's doable and it works. You could also do something like this, where you store alongside every hand gesture the list of hand gestures that this hand gesture will win against, which is very easy to check whether or not who won with, but it requires knowledge of what a hash map is, or a map in Java. But I've got an algorithm that beats both of those, and I'm going to show it to you. So first, I drew a simple little graph of rock, paper, scissors, and I have an arrow pointing from each of the hand signs to the hand sign that it wins against. For example, rock beats scissors, scissors beats paper, and paper beats rock. Now, there's one thing that I want you to notice about this graph, and that is for all of the matchups that don't include matchups against the same hand gesture, for each hand gesture, it wins half the time, and it loses half the time. Paper wins half the time, loses half the time. Scissors wins half the time, loses half the time. Keep that in mind. I'm going to explain the actual algorithm with this graph of rock, paper, scissors, lizard, Spock. And again, it's important that you notice that for every hand gesture, it wins half the time and it loses half the time. That's for every one of these. Now, if you'll see too, I've labeled with starting at rock is 0, paper is 1, scissors is 2, Spock is 3, lizard is 4, and I've done that just to give an order to these. This is the order that you're going to be storing them in code for the algorithm. So let's say that two people, player 1 and player 2, are playing a game of rock, paper, scissors, lizard, Spock. And let's say player 1 chooses rock and player 2 chooses scissors. Now, here is the algorithm to check who won. If the two players chose the same hand symbol, then it's a tie. Otherwise, we count from what player 1 chose up to what player 2 chose, and we keep track of the number. That's 1, 2. If this number is an even number, then the player 1 wins. Otherwise, player 2 wins. So in this case, if player 1 does rock and player 2 does scissors, because we counted up 1, 2, and that's an even number, player 1 wins. Now let's do another example. Let's say that player 1 chooses Spock and player 2 chooses paper. So we count starting from Spock around and going up by numbers 1, 2, because this is going to wrap around 3. So that means that because that's an odd number, player 2 wins against what player 1 did. And this is going to be true for every matchup that you can possibly imagine. And this works with this ordering of items: rock, paper, scissors, Spock, lizard. Now, an illustration of what that looks like in pseudocode. This is not Java, this is pseudocode, English that it should be easy to translate into Java code. So if you can see up top, the ordering for the gestures for rock, paper, scissors will just be rock, paper, scissors. And the ordering for the gestures for rock, paper, scissors, lizard, Spock will be rock, paper, scissors, Spock, lizard. And then we're going to declare two variables. Player 1, P1, that's the index of player 1's gesture into this list of gestures. That's going to be a number. And P2, that's going to be the index of player 2's gesture into the list of gestures. Now, if P1 and P2 are equal, it's going to be a tie and we don't even have to do anything. Otherwise, we are going to calculate this distance formula. And this is going to be a very simple calculation with a modulus operator. So P2 minus P1, that's like counting forward from P1 to P2 and getting that number. That's what that means. Plus gestures, plus the number of gestures in the list, modulo the number of gestures. And we're doing the plus gestures, modulo gestures, because we are cycling around, and if we somehow get into a negative distance, we actually have to put that in the range of 0 through 2 or 0 through 4. And once we get that distance, if the distance is even, then return player 1 because player 1 won the game. Otherwise, return player 2 because player 2 won that game. So that algorithm will not only work for rock, paper, scissors and rock, paper, scissors, lizard, Spock, but it will also work for any generalized rock, paper, scissors game, so long as for every symbol it wins against half of the other symbols and it loses against the other half. And just to prove this to myself, I went and I looked up a bunch of different variations of rock, paper, scissors that use even more symbols than 5. And all of them have some ordering that you can use with that algorithm that works. So I found this website, umop.com/rps.htm, and it's a page by this rock, paper, scissors enthusiast, apparently, who came up with a whole bunch of different versions of rock, paper, scissors. And as you can see, there's one with 7 symbols: rock, paper, fire, air, scissors, water, and sponge. And he also has a chart showing how that works on his website. And for his 9 game, he takes the last game and he also adds the signs for human and gun. For rock, paper, scissors 11, he takes the ones from 9 and adds devil, and this is a really hard one to do, excuse me. Wolf. There we go. You can see that. That's the wolf. And then for rock, paper, scissors 15, he takes those symbols and he adds a snake, this is really hard too. Dragon, lightning, and tree. So all of these, by the way, all of these lists of words are in the order that will work with my algorithm if you want to put these in your game. And he also has a 25 symbol game. He has symbols for each of these. There's all the ones in the previous one, plus a nuke, a cockroach, dynamite, a bull, an alien, a monkey, an axe, the sun, the moon. Like, it's crazy how complicated this game gets. And this, by the way, is also in the right order to use with my algorithm. And you can check that out at this page if you'd like, umop.com/rps25.htm. And he also has a 101 symbol game, but I'm not touching that with a 10-foot pole. But because it also works in the same way that the other ones did, then in theory that could also work with this algorithm. So I really hope that this helps you in your next assignment. If you have any questions, either leave a comment below or talk to me in the discussion board or set up a Google meeting with me, whatever, you know? And if anybody else understands and can help somebody else, they can go ahead and do that as well. And I would just like to say good luck on your assignment, classmates. Take care.